Blog Talk Radio.
Welcome to the AME Food Testing Show. Today's topic, continuous ultrasound treatment with chlorine washing, with Arne Pearlstein, Ph.D., and Feng, Ph.D., Innovative Food Science and Emerging Technologies, University of Illinois. Arne Pearlstein received all of his degrees, bachelor's, master's, and Ph.D. at UCLA in engineering. He's a professor in the Department of Mechanical Science and Engineering at the University of Illinois at Urbana-Champaign. His research is in the area of fluid dynamics, and his work has been supported by the National Science Foundation, the Department of Energy, NASA, the Office of Naval Research, the Air Force Office of Scientific Research, several corporations, including IBM, and now by the U.S. Department of Agriculture. Dr. Feng is an associate professor in the Department of Food Science and Human Nutrition at the University of Illinois at Urbana-Champaign. He has concentrated his research over the last 10 years on applying novel chemical and physical methods to enhance microbial safety of fresh produce. In the past 7 years, Dr. Feng has worked on 4 USDA-supported projects totaling almost $1 million, and with a fresh produce processing equipment manufacturer to develop new food safety innovation technologies for fresh produce. His team has worked over a dozen leafy green vegetables and fruits using different sanitizers and physical sanitation methods. Now, welcome with me, Drs. Feng and Pearlstein. Gentlemen?
Hi, Andy.
Hi, Andy. This is Hao.
Welcome to the show. I'm very excited about today's topic and wondering if we could have you update us on your latest activities.
Yes, we recently have just developed a new method to treat fresh produce to increase the efficacy in the microbial reduction.
Very good. Let's get right into our topic. What are the bacterial pathogen risks inherent in fresh vegetable production?
In order to answer this question, I would like to first look at a few set of data published recently. In the past 30 to 40 years, we have seen a continued increase in the production and consumption of fresh produce. For example, in 2010, the value of fresh fruit and vegetable consumption reached $122 billion in the U.S. From the data published by the U.S. Census and USDA. And from that, you can imagine if we have about the same contamination rate, then you'll see an increase in the chance of outbreaks. Actually, from the data of CDC, Centers for Disease Control and Prevention, this is a report in 2008. Between 1996 and 2005, the leafy green consumption in the U.S. increased 9%, while leafy green associated outbreaks increased 38.6%. So we have high increase in the number of outbreaks compared to the consumption of produce. This might be caused by the more rapid reporting system we have now. So now we want to know probably what does the risk come from. Actually, it can be at any point in the continuum growing, harvesting, packing, processing, and handling of fresh produce. So there might be a chance for microbial contamination at any point in this field to fork continuum. So this makes the risk reduction pretty challenging. So I want to probably present another side of the story. I think it sounds to be pretty scary. Actually, we want to look at how high is the risk. According to the report from the United Fresh Produce Association in 2006, at that time, there were about 6 million bags of green leafy salad sold per day in the U.S. If you add the number together, it's about 2 billion bags per year. So according to the CDC numbers, roughly each year there are a few hundred people got sick because of consumption of leafy green produce. So if I compare the numbers, a few hundred cases per year versus 2 billion bags per year, the chance for any individual to got sick is very, very low. With that said, we know that one death is too many, and one outbreak is too many for everyone, for the family, for the industry. If you look at the societal impact, economic impact, we do want to prevent the outbreaks. That's why we are working hard, trying to develop new sanitation methods to be more effective, to reduce the risk of outbreaks.
So this is a problem not just from the standpoint of direct morbidity in an outbreak, but also as a result of the fact that after these outbreaks, consumption of leafy green produce is depressed for months or sometimes years, which means that people are eating less of these healthy foods and presumably more of less healthy foods, and that has effects on a number of other diseases over a much longer period of time.
Excellent summary of the challenge, gentlemen. What are some of the common risk minimization strategies that food producers have engaged to minimize the risk of bacterial pathogens on their products?
Currently, the prevention is still the most effective and the most important method. The good agricultural practice, or GAPS we call it, has played a very important role in microbial safety hazard prevention across the continuum of growing, harvesting, washing, packing, and transportation of fresh produce. GAPS implementation and GAPS audits are very common practice now in the produce industry. So actually, this is probably the most important method to reduce the risk. And also the training, education is kind of important. However, we know that contamination cannot be prevented 100% of the time. So sanitation or decontamination is still very important in case you have some pathogen somehow landed on the surface of produce. So currently, the produce industry using washing to remove the dirt, debris, or microorganisms, and maybe organic matter from produce surfaces. In that case, we add chlorine in the washing water to wash the produce, and we can remove up to 1 or 2 log units of bacteria, which is about a factor of 10 to 100-fold reduction in the number of pathogens. That is widely used now.
So the wash water and combination with chemical treatment. So
right.
In studies, what is continuous ultrasonic treatment?
Where this study conducted here in the Illinois, we trying to develop a continuous flow system with ultrasound capacity, and in the treatment combine both chemical sanitizers and ultrasound to reduce the number of pathogens on the surface of fresh produce. This is project started in 2008, right? 2008. So we have developed a pilot scale system here in the pilot plant. We have done a whole bunch of studies, experiments here with different produce. That's basically the project itself.
So by pilot scale, how means it's our washing facility is approximately 3 feet wide and about 10 feet long, and the continuous aspect of it is absolutely critical here. In principle, you could do this in a batch process, and people have done this in the laboratory in a batch process. A batch process would be where you dumped some number of pounds of spinach leaves or shredded lettuce or whatever into a tank of water and then hit it with ultrasound. And then after some sufficient period of time, you took it out and dewatered it and continued the process. But that's not what goes on, and that's not really consistent with what goes on in a modern lettuce or spinach processing plant where stuff comes in on a belt from the truck at one end and then goes off on a belt to a dewatering and packaging line farther down. And what happens in between is this sanitization step. And so the idea is that if you want to do ultrasound in an industrial setting, you really need to do it as part of this continuous process where the product is continuously moving in suspension in water past the ultrasound. So that is exactly what we've done. We've in some sense strapped on ultrasonic transducers to the sides of the washing channel, and as the letters to the spinach or whatever it is goes through, it is continuously exposed to ultrasound from the beginning of the channel through to the end without ever stopping, without any intermediate handling, without anybody doing anything in between the time it enters and the time it leaves.
Excellent, gentlemen. Can you offer a little more description on the type of ultrasound, the intensity of the ultrasound, and the penetration on the product, and if there's any denigration on the product?
I think this is a good question. Actually, there are two types of ultrasound. The one we're talking about here today is the one we call high-intensity ultrasound. The frequency is anywhere from 20 kilohertz up to 100 kilohertz. The energy level is relatively high compared to the ultrasound we use in medical imaging. So in that case, we for example, for this specific system used in our lab, we have three frequencies: 25 kilohertz, 45, and 40 and 75 kilohertz. That is the one we use in this system. Basically, it can produce small bubbles in the liquid, and those bubbles can generate some localized physical and chemical effects to help to remove the bacteria on the surface of produce. But of course, there are some technical issues will have to be solved before we can move forward to do a sanitation.
Yeah. So one of the problems here is making sure that each leaf, and in fact each side of each leaf, is more or less uniformly exposed to ultrasound. If a given leaf or a given leaf side does not get enough ultrasound, we don't get enough bacterial kill. Whereas on the other hand, if there is too much exposure to the ultrasound, there will be damage to the product. And so to do this in a fairly dense suspension of lettuce leaves moving through this 3-meter channel, 3-meter long channel, 10-foot long channel, is a significant challenge. The transducers are on the sidewalls of the channel, and so product which is near the sidewalls is going to get hit fairly well by the ultrasound, whereas product which is near the center of the channel is going to get relatively less exposure. So it is critical that we have good mixing across the width of the channel, and that we try to achieve using some water jets, conventional water jets, and we have some other approaches to doing that also, but the water jets at this point are the primary means. People have suggested that we use bubbling, but the problem with bubbling is that is really not consistent with doing ultrasound. That would be fine if there was no ultrasound, but with the ultrasound, the bubbles scatter the ultrasound very significantly.
Well, gentlemen, that's an excellent description of your pilot project. Can you enlighten us on some of your preliminary results of your method?
Yeah, we have run a number of experiments trying to look at the efficacy of this new method. In one experiment, we washed spinach, baby spinach, with E. coli OY57 inoculation. In that case, we look at two cases. First, we want to see what is the potential of this technology to reduce the number of E. coli. So that way we just use a single leaf without any blockage of other leaves. So with this kind of setup, we can increase the reduction of E. coli by 90% compared to a chlorine alone wash, reaching a maximum conduction of 4 log units. In another experiment, we use a whole bunch of leaves. We call batch leaf wash. In that case, we have blockage from other leaves. With that setup, we can achieve an increase of about 70% compared to a chlorine alone wash in terms of E. coli. We also test other bacteria like yeast and mold, and also the natural flora. So this is spinach wash. In another test, we use lettuce, romaine lettuce, also inoculation of E. coli. We look at the effect of different power level, ultrasound power level, and we can also achieve 4 log cycle reduction in the number of E. coli. For, let me see, romaine lettuce, and for iceberg lettuce is pretty similar. You can get 3.98 log reduction, which is about 4 log reduction. So that is the data we have now.
So 4 log reduction is a reduction of 99.99%, which is pretty good.
Well, gentlemen, you're getting close to the sterility standard. Can you let our audience of food production, food quality, food safety, and food security managers kind of get an understanding of what's the potential for this new application of technology?
Well, we see this as being applied in large-scale processing of leafy green vegetables, and the fact that we've been able to make this into a continuous process, I think, is a huge advantage from the standpoint of both space and time. Most processing facilities are space limited, and there is not really room to stick in an additional step. So to the extent that conventional washing facilities can be, let's say, retrofitted with ultrasonic transducers on the sides or on the sides and the bottom, that can be done without adding any additional step into the processing line, and also without increasing the residence time or the processing time, which is also of considerable interest to people that operate these large-scale facilities. In addition, we've made some preliminary steps in terms of washing whole heads of lettuce, in other words, before it is shredded, and I think Hal will talk about that a little bit later.
Yeah, in terms of the potential, I think we can incorporate this technology into current washing systems, washing lines, with increased efficacy, and at the same time, we are going to introduce some additional capital costs. I think that is a practical issue we have to take into account. We haven't done anything to look into economics yet, but we're expecting probably we're going to have some additional capital investment into this.
There are also some additional operating costs in terms of electrical power and a little bit of extra cleaning, but on the other hand, to the extent that this process is able to possibly reduce the amount of chlorine that is used, that would be a significant step towards, number one, reducing chlorine consumption, which is really no longer allowed in vegetable processing in the European Union, and sooner or later will probably not be allowed in the U.S., and also in terms of reducing water consumption, which is of considerable interest in California, where a lot of leafy green vegetables are grown.
So, gentlemen, if I could summarize, you're essentially looking at a capital cost to install your equipment, some adjustment to the protocol depending on the product, and your only consumable is electricity. Is that what I'm hearing?
Yes.
Excellent. Can you talk about any other projects or studies that you're currently engaging in at the University of Illinois?
Yeah, we do have a few number of other projects. One is joint project with a team in the USDA. In that case, we're looking to a different washing strategy for head lettuce. So currently, the head lettuce is cut into slice or stretch before sanitation wash. And this approach increases the organic load in the washing solution and creates large surface areas, and of course can introduce potential microbial contaminants into the interior of produce, so contributing to spread the contamination. So right now we propose a new strategy. It's from USD team actually. We want to wash the whole head lettuce before cutting, and so we have done some experiments with E. coli inoculation with chlorine and with Tsunami, which is a commercial sanitizer. So what we find out is that if you wash the produce before cutting, you can get more log reduction compared to the traditional cut and wash process. For chlorine, if you do washing and cutting, you can get 2.2 log reduction. But with the traditional cut and wash process, you get 1.5 log. So it's 0.5 log increase in the log reduction. That is about 70% increase. So I think it's pretty good. In another project, let me see, we are trying to develop some new sanitizers. For this specific, we have done a whole bunch of experiments, but for this one, we combined a new surfactant, which is, let me see, thiamine dilaryl sulfate, or TDS, in combination with malic acid. With this combination, we can achieve over 5 log reduction in the number of E. coli 0157 on spinach and lettuce. For example, with 1% TDS, which is a surfactant, and 4% malic acid, and you wash for 1 minute, we can achieve 5.58 log reduction on the surface of spinach. For lettuce, same concentration, 1 minute wash, well, we can eliminate all the E. coli, basically. We cannot detect it. So I think it's pretty effective. And this surfactant TDS is a nutrient fortifier in Korea and is a dietary supplement in Japan. In the U.S., I think it has been just granted self-affirmed GRAS, which is generally recognized as safe status in the U.S. And the malic acid is also GRAS substance. So we think it's a pretty effective formula. So we're happy with this. This is another one. So we also look at the some fundamental issues in produce wash. We want to look at the interplay between the bacteria, the produce, and washing solution. In that case, one thing we'll be doing now is to develop some artificial plant surfaces. In that case, we have some reusable surface. We can minimize the variation among the samples. That way we can find the correlation between the produced surface chemistry, surface topology, and the sanitizer chemical solution properties. And hopefully you can develop some new method, more effective sanitation method.
Well, gentlemen, it sounds like you have some exciting research possibilities. I'd like to return back to our main topic in our concluding remarks. My major question is, it's a question I always have when I hear about cutting-edge technology and near-sterility standard results. What is the potential commercialization of your continuous ultrasonic treatment, your method, and your equipment in the near term?
I think we need to keep improving the system to minimize the blockage of leaves, because if you watch large quantity of produced leaves, the blockage will be an issue. So we need to keep improving the design and to further reduce the blockage. That way we can further increase the log reduction. That is one technical issue we have to address. And at the same time, we need to work with the produce industry to do more testing, to test other organisms. Right now, we have been working with E. coli. We may want to look at the Shigella and some other bacteria. And that's just something we need to do before going into commercial production.
So that the blockage that Hao refers to is a critical issue. You can visualize this in terms of doing, let's say, medical imaging with X-ray or ultrasound or whatever. If you've got two organs that are lined up with each other, the one that's behind the first one isn't going to receive very much X-ray or ultrasound, and you're going to have a hard time imaging it. Well, it's the same thing here. What we have is in a dense suspension of lettuce or spinach leaves, the ones that are near the middle of the channel are blocked by the ones that are closer to the walls where the transducers are. And so we think that we can overcome this by better mixing, and we're working on that, and we hope to achieve a major improvement there sometime this coming year.
Excellent, gentlemen. I was wondering now if you could conclude your remarks by offering any encouragement to our audience, again, of food producers, on the potential of hopefully eliminating these food pathogens in their production, and as your research leads you toward those results, what further steps they can take at this time.
Yeah, I think the key now is to use combination of different sanitation methods or probably sanitizing agents. In our case, we're trying to combine the chemical sanitizer with a physical method, which is ultrasound. Probably we can achieve additive, maybe even synergistic effect to increase the efficacy, and I think this is the way to go in the future. So in terms of ultrasound, it is a pretty, I think, clean technology in terms of image compared to other sanitation methods, and because it's widely used in medical imaging. And we have found out that it is more effective compared to a chlorine alone wash. And of course, we need to spend more time to improve engineering design, but we are I think we are I think it's pretty promising technique. Just need to have more research development effort and probably work with the produce industry directly, and also work with the consumers, trying to incorporate some education programs, work with farmers, producers, and then in that case, well, I think we can probably develop a more effective sanitation method to reduce the risk of foodborne illness disease.
The image or perception problem that Hao refers to, I think, is quite important. Gamma radiation, for instance, is a pretty good way to kill a number of different bacteria, but it's ionizing radiation, and people associate that with nuclear fallout, mutation, that sort of thing. And on the other hand, chlorine is associated with organochlorine compounds and trichloroethylene and this kind of stuff, even though it's got really nothing to do with it. And that also has a public perception problem. So to the extent that things like ultrasound, which, as Hao said, is used in medical imaging, and things like thiamine dilauryl sulfate, which is a vitamin B derivative, can be used. These are much more benign and have much less of a public perception problem, and hence will be much more likely to be publicly accepted.
Excellent, gentlemen. I would now like to allow you closing remarks as we conclude our interview. Gentlemen?
Well, thanks a lot, Andy. It's been great talking to you, and we appreciate the opportunity to present this work.
Yeah, thank you, Andy. Thanks, good.
Thank you very much, gentlemen, and look forward to hearing about your future research. And as this particular project with continuous ultrasound comes to the point of commercialization, so the audience can engage if it's potentially valuable for them in their processes to, again, produce safe food for consumers. Thank you, gentlemen, and have a great day.
Thank you, Andy.
Okay, thank you. Have a nice day.
Bye now.
Bye-bye.